All right.
Maybe we should go and draw a handprint. Push here,
So where would you draw the handprint?
right there. Would you like me to come draw it for
Use
you?
words.
I make a good turkey hand. On this, so you got your door. It's right here.
Yep.
Yeah.
Oh, so you're tucking it over here,
Yeah.
not here.
Mm-mm.
All right. Recognize what's going on here. All right, so if I push over there, you're saying I'm going to close the door on the white side.
Mm-hmm.
You know I've got something else.
Mm-hmm.
How should I push?
Push it towards the brown side.
Push it towards the brown side.
Yeah, with the cardboard.
Push towards the door frame.
All right. So even that's not going to be the most efficient there. So we go over here, push it towards the door frame. This still wasn't the most efficient way of doing it.
I feel like this is like trying to program an AI to close it.
In what direction should I push in general? We've established I should push farther away from the hinge. I think we've established that.
Some sort of angular velocity.
What was that?
It's in an angular velocity.
So you said consider the angular velocity, or so that there is an angular velocity?
So that there is an angular velocity.
Okay, I will accept that. I mean, the torque is going to cause angular acceleration, and angular acceleration should cause a change in velocity. Therefore, if it starts at rest, it'll start moving. Doesn't matter how I push from this side. How, Coy?
It has to be towards the frame at all times.
Towards the frame at all times. So if the frame is here, it's most efficient for me to push like that.
It should be
Perpendicular to
perpendicular.
There's the key word. I get the most bang for my buck if I'm pushing perpendicular to the door. I need some way of expressing this so that it is a maximum when the push is perpendicular and when I'm farther away from the hinge or axis of rotation. Huh, what a coincidence. We just talked about something in which we get a maximum value when things are perpendicular. Torque. How hard I push matters. This is the force. This is the lever arm or moment arm. We'll flip back and forth between those. And the cross product ensures that I get the most impact from perpendicular. So this is deals with relative angle. So if I have a door here with a hinge at the end, I'm going to make up a number here. Let's just say 4 kilogram meters squared is the moment of inertia. If I apply a force here of 3 newtons, so that's perpendicular, 3 newtons, then the torque that is going to be applied, well, my force is 3 newtons that way. My lever arm is from the hinge, the axis of rotation, to where the force is applied. That's R. Come up with a number there. Let's just say that the magnitude of R is 0.7 meters. So the torque that's being applied, again, it is a vector. It has a magnitude and direction. It is going to be the magnitude of the torque. It's going to be RF sine theta. Now, when determining the angle, you put them tail to tail. So R is pointing in that direction, F is pointing in that direction. That is a right angle. So 90 degrees. So I have 0.7 meters times 3 newtons times the sine of 90 degrees. Which is 2.1 what? When we dealt with Newton meters before, that was a joule. This is not a joule. Joule is specific to work and energy. Newton meter here is just a Newton meter. The direction of the torque. Well, we have our R cross F. I put my hand in the direction of the first vector, and then I bend it towards the second vector. My thumb points out, and so the direction of the torque is out. Or, look at it from this point of view, I have a door right here. If it's at rest and I push on it like that, it's going to rotate this way. My thumb points out again. So if I establish a convention here of I hat, J hat, K hat, then it'd be 2.1 Newton meters K hat. Questions to hear?
Pretty sure. Start this up again.
Yeah. All right, let's take our newfound knowledge and apply it to a chapter 4 kind of problem. I have a beam being held up by 2 sensors. I'm going to call this tension is F sub L and F sub R. I have a 5 kilogram mass here. The weight of the beam, mass of the beam is 10 kilograms. And then at this point right here, I have a 2 kilogram mass. The total length of this is 10 meters. We'll say that's 1 meter. 2 meters. 2.5 meters. 4 meters. Uniform beam. What are the two tensions that are holding up the beam?
Like, what are their values?
Yes. Now, if we were doing just chapter 4 or chapter 5 stuff, we would be able to come up with one equation with the sum of the forces up equals the sum of the forces down. I guess I did not state this, but equilibrium. Linear and rotational. And if I just looked at the sum of the forces up first is equal to the sum of the forces down, that's only one equation and I have 2 unknowns. And so now we can bring in the rotational equilibrium bit, we can bring in the torque, and we can actually solve this. I don't have it, I've just erased it, so let's go ahead and stick up a convention here of I hat, J hat, K hat. For the sake of ease, let's just put this on some mysterious planet. where the acceleration due to gravity is 10 meters per second squared. So as we've done before, start out with the force diagram. I have FL up, FR. I've got 50 newtons down here. I have 20 newtons here. And then from the weight of it, it's a uniform beam, so the center of mass is smack dab in the middle, and that would be 100 newtons. I don't have to break anything up, it's all vertical. My equations of motion, F equals ma. I made a positive over there, so this becomes FL plus FR minus 50 minus 100 minus 20 is equal to 0. All right, I zipped through that because that's chapter 4 stuff. Questions though on how we got this equation?
The 100 is the weight, right?
Yes. Right. So now we need another equation. I got one equation, 2 unknowns. I need a second equation. There's nothing in the I hat direction. So I could do an I hat equation. Here's what the I hat equation would look like. My I hat equation. 0 equals 0. A true statement, not real particularly helpful. But we do have a K hat direction, K hat. Because we have torque involved here. So, torque R cross F for the individual torques. The total torque is equal to I alpha. But because it's in rotational equilibrium, there's no angular acceleration, so that's going to be equal to 0. But the individual torques R cross F, so R is the moment arm. It is a vector from our axis of rotation to where the force is applied. But what is the axis of rotation of this for something not rotating?
Is it the center of mass?
Okay? Why?
I don't know.
Go for it. Somebody, why? If we establish the middle as the axis of rotation, what would be the reason? Coy?
Because Cooper said so.
Yes, that's the reason. We can pick any place that we want. It is generally recommended to pick some place where the torque will be 0. To pick some place where we will eliminate one of the torques. If we pick smack dab in the middle, then the 100 newtons from the weight does no torque at all. So let's do that. That.
You gonna throw a tantrum today?
Axis of rotation. Now, let's do the torques. I've got 5 forces here. Officially, I have 5 torques. One of the torques will be 0, but we'll start on the left-hand side. We've got that 50 Newton force right here. What is R? What is the moment arm for this 50 Newton force?
4 meters.
It's 5.
No, it would be, I'm good with 4 meters. But he stopped too short. But it makes me forget.
Vector?
Yes.
Is it K hat?
No, it's a vector from here to here, it's just pointing that way.
Oh. Negative I hat?
Yeah. So the first one is negative 4 meters I hat cross. That's 50 newtons, negative 50 newtons J hat. All right, that's the first one. The next one. What is R hat?
Negative 3 meters I hat.
Cross FLJ hat plus, we'll do the middle one, that's 0 to 0 vector cross 100 newtons, negative 100 newtons J hat. Negative 100 newtons J hat. That's going to be 0. Plus, working our way over, we have that 20 newtons. What is the motor for the 20 newtons?
1 I hat, 1 meter I hat.
Cross 20 newtons, negative 20 newtons J hat. Plus one more FR. I guess 2.5 meters I hat cross FRJ. And that sum should be 0. All right, now it's just a matter of cranking through it. I'm not gonna write units till, well, ultimately, the answer is gonna be in newtons. But, all right, so negative 4 I hat cross negative 50 J hat.
200?
Positive or negative?
Positive.
Okay, why?
Because it's negative, not negative.
And,
That makes positive.
I had.
Okay.
J hat.
that's the other piece. Don't forget, we got these two negatives here, but there's also this I hat cross J hat, which is positive K hat. So we got two negatives and a positive. All right, so we got 200 plus I cross J. What is I cross J?
Take.
So I got minus 3 FL. Starting on the wrong level there. All right, plus 0 plus negative 20 plus 2.5 FR equals 0.
So, if we were writing units in this, would we need to put K after all the answers? To establish that's the direction of it?
Yeah, technically there'd be all K hats all the way across the board.
Isn't it minus 2.5 of FR?
This one,
Yeah.
I is that way. I mean, the force is that way, and, or, the moment arm is to the right and the force is up.
Oh, it's up. Okay.
Now, another way that we could have figured out whether it's positive or negative is, if that's my pivot point right there, which way are the arrows going to rotate it? Well, this 50 newtons right here would rotate it clockwise, or sorry, counterclockwise, thumb points out positive. The FL would rotate it that way, clockwise, so it's negative. That's not gonna rotate it. This 20 newtons would rotate it also, clockwise. I don't know why that's difficult. So it's negative, and this would rotate it that way. Again, that's the pivot point, this would rotate it around like that. Positive. And so we are left with 180 minus 3 FL plus 2.5 FR equals 0. And now with two equations, two unknowns, let's solve it. I guess on the first one, we can solve for one of them, so FL is equal to 170 minus FR. And then on the second equation, I get 180 equals 3FL minus 2.5 FR. Is equal to, it's 51, 510, minus 3 FR, minus 2.5 FR, distributing. So I get 5.5 FR is equal to 330, I think. What is this? Bless you.
Bless you. Thank you, good God.
60.
60? And so FL, well, I know that 170 minus that, so FL would be 110. Let's see if this makes even some sense. The 100 newtons is closer to the right side by ½ meter. But we have this 50 Newton over here, which is definitely closer to this one. The 20 Newtons closer to that. I would expect, just from the inspection of this, that this would be bigger than that is, which matches what we have over there. This is 110 Newtons going up, and this is 60 Newtons going up. Now, what could we have done to simplify the math?